Today, we find ourselves in a global energy crisis. The cost of living is high and our carbon footprint is problematic. One way to help is by retrofitting old buildings to make them more energy efficient. But this raises a problem. We need to effectively and efficiently predict the energy consumption of a given building. And so we present a solution through machine learning. If we can predict energy usage faster and cheaper, we can better improve people's standards of living.
The model was coded in Python using a Jupyter notebook and stored on Google Colab so that all members could contribute remotely. From the input data given, we created a categorical train set data. From this, bad columns with NaN values were dropped, as well as filling out the appropriate weather data. As we used a decision tree model, we did not have to normalize the data because this model is not distance-based and functions by partitioning the data to make predictions.
We choose the decision tree regressor because it handles both categorical and numeric variables. We decide not to convert our large categorical ranges into numeric values using hard encoding. It can result in a high number of dimensions and leads to computation expense and overfitting. In addition, it allows us to spend less time understanding the complex scientific factors involved in the relationship between variables.
For our regression task, we opted for root mean squared logarithmic error as our evaluation metric instead of typical accuracy-based metrics like R2 score. We made this choice because our decision tree effectively handles data without regularization or normalization, and our features also span a wide range. As a result of that, RMSLE was a more appropriate measure of error for our needs and was more robust when dealing with outliers overall.
When building a decision tree model, selecting the right values for hyperparameters like maximum depth and maximum lift nodes is crucial to prevent overfitting. We experimented with different hyperparameter values and discovered the sweet spot where the training error reduces while the validation error initially decreases but then starts to rise. The approach helped us avoid overfitting and achieve better overall performance.